This is a video on mathematical proof with a focus on proof by contradiction. So proof by contradiction is basically when you want to prove a statement, but it's hard to prove it directly. So you instead try to prove the opposite of that statement. And then you run into kind of a roadblock or a logical contradiction. And that means that the statement that you're trying to prove, which you kind of knew wasn't true in the first place, can't possibly be true, leading you then to a proof for the truth of the original statement before you took your contrary position. Okay, so glad that we got that there. Let's have a look at an example. The example that I'm going to look at is proving that root 2 is irrational by contradiction. And this is actually an examinable proof on your course, so you have to know it for your Leaving Cert exam. Okay, now since this is proof by contradiction, we're going to actually make the assumption that's completely opposite to what it is that we're trying to prove to begin with. So we'll state that first. We're going to assume that root 2 is rational. So if that's the case, it means that we're able to write root 2 as a over b, where a and b are integers and b is not 0. It's important too to realise at this stage that this a over b that we say is the form for rational numbers assumes that the a and the b have no common factors, so that this is as cancelled down as this fraction can get. And this is actually a really important part of our proof, so it's really important to include it as part of our statement at this stage. So then we kind of start to mess around with this equation here. So if root 2 equals a over b, well, we could square both sides. And this would give us 2 equals a squared over b squared. And we could move things around a little bit more. We could bring the b squared up here and multiply it by the 2. So we could say that 2b squared equals a squared. So this means that a squared must be an even number since it's twice something else. So we'll state that a squared is even since it has 2 as a factor. Well, interestingly, if it's true that a squared is even, well, that also means that a is even because only even numbers can square together to give an even result. So we'll state that a is even. You can test this yourself by squaring a few odd numbers and seeing what happens. So if a is even, let's define a as an even number. So we could call a 2c, 2 by something. And now let's go back and look at a squared again. Well, if a is equal to 2c, that implies that a squared must be equal to 4c squared. That's just squaring your 2c, so squaring the 2 and squaring the c. But I already had a name for a squared. I already was able to say that a squared was equal to 2b squared. So now I can say that a squared is 4c squared, and it's also 2b squared. Okay, so let's ditch the a part of it for a second and just focus on the second two parts of that equation. So if 2b squared is equal to 4c squared, well, I can divide that across by 2 and say that 2c squared equals to b squared. But if I follow the same logical steps previously, when I had 2b squared being equal to a squared, well, that let me know that a squared was even, and that meant that a was even. So if I've got a similar statement here for c and b, I could say, okay, well, that means b squared is even. So that tells me that b is even. Notice I can save myself a little bit of writing here because I've gone through a set of steps to get to a similar conclusion previously. So I can kind of take a bit of a shortcut this time around. Okay, so now this is interesting because I've got two statements now about a and b. I've got the statement that a is even and the statement that b is even. But if I look back to earlier on, when we had made this assumption that root 2 was rational, we had defined root 2 as a over b, and we had specifically said that if that's the case, a and b have no common factors. However, if a is even and if b is even, well, even numbers all have a factor of 2. So we run into our roadblock. So I'll point this out and I'll say, but this means a and b have a common factor of 2 if both are even. This contradicts our initial assumption. And our initial assumption, if we glance back, was to assume that root 2 was rational. So we've contradicted this assumption. And if we've contradicted this assumption, well, this means that root 2 can't be rational. So we'll finish off by saying, therefore, root 2 is not rational, and then just qualifying that as it cannot be written as a over b, where a and b have no common factors. It's quite a long proof. You do have to know it.